as soon as it says it's starting. All right, I think it's starting now. Yep. All right. So, hey everybody. I want to start things off real quick, just making another announcement. I know on Google Classroom I said I was going to make the quiz due Sunday. I've decided I'm going to push it back to make it due Monday at midnight. And one of the reasons why I want to do that is I want to give you guys a window of time on Monday where I'm going to set up a Google Meet. So if you're doing the test, or sorry, not the test, if you're doing the quiz on Monday, and if you tried doing the quiz a little bit over the weekend and you had a question about something on the quiz and you just wanted to get some feedback from me, like in this kind of a setting and not via email, I wanted to provide that for you guys on Monday. So I'm going to set up a time Monday during the day for you guys to be able to just hop on here if you're doing the quiz and you want to get some extra, or you just want to ask a question while you're doing it. You can hop on, hop off. It'll be just a window of time available for you on Monday. So just wanted to let you know that, because I'm probably going to post the quiz later today and let you guys have today, tomorrow, Sunday, and then Monday to work on it. But I am probably still going to post something on Monday, like a do now or another video or something later in the day. But I probably won't make the video. You can watch that Monday or Tuesday probably. So just to let you know. So how was this section, guys?
Not a fan. Not a fan.
Yeah.
I hate trigonometry.
Well, it's new. We're starting to hit some of the stuff that's a little bit different than what you've done. Some of the stuff you did in this section probably seemed very familiar, and some of it was completely foreign in some ways. But I definitely want to break some things down. I had several of you asking me questions about a few of the checkpoint questions, and specifically in the quiz review, a lot of the ones that were having you use trigonometric identities to transform a side of an equation. So I'm going to go ahead and present, and I'm going to show you guys the solutions to the checkpoint problems. I'll go through it slowly, and you can check your solutions, and if you have any questions about the checkpoints, I can walk you through something with that, and then I'll go through all the quiz review questions and show you the solutions for those, including the ones that are trigonometric identities that didn't have solutions in the back of the book. All right?
All right.
Okay, so I'm going to start presenting here. So let's see. All right, does everybody see the smartboard thing with checkpoints at the top?
Mm-hmm.
All right.
Yes.
So this is the first checkpoint for example 1. So if you want to get your problems out there, if any of you have questions about this one, number 1, they give you a triangle in that problem and tell you 2 of the 3 sides and ask you to find all 6 of the trig functions, and these were the solutions for that. Some of you might have figured out that the triangle itself is a 30, 60, 90 triangle based on the relationship of the short side and the hypotenuse. That was kind of one of those, if you see it, that makes the problem a lot easier, but it's not always obvious. All right, so I'm going to jump on to checkpoint number 2. This one asks you to find the values of the cotangent of 45, secant of 45, and the cosecant of 45. In the textbook, they showed a picture of the 45, 45, 90 triangle, and you could have labeled the sides opposite, hypotenuse, and adjacent if you wanted to, and then made the fractions from there. That was already given in the textbook. Number 3, they ask you in the checkpoint to use the equilateral triangle shown to the left on the page to find the values of the tangent of 60 and the tangent of 30. Tangent of 60 ends up having opposite over adjacent. Opposite side is square root of 3. Adjacent side is 1. That's why that's that one. And tangent of 30 was, again, opposite over adjacent. 1 over the square root of 3, which you had to rationalize to get this one. So I expect 1, 2, and 3 were probably pretty easy. Was that the case for you guys for checkpoints?
I didn't get any of it. But
It's all based on the opposite. It's the SOHCAHTOA stuff. And there was a diagram of all that information on page 277 in your textbook. I talked through the 3 examples for these 3 checkpoints in part, I think it was part 1 or 2.
okay. I'll have to like
YouTube
rewatch
videos.
this.
Yeah, the YouTube videos for parts 1 and 2. And then checkpoint 4. I think that one was, you know what? That one was part 2. It was checkpoint number 4 and example number 4. I talked about the degree, minutes, and seconds form and the cofunctions in that video, and changing from degrees, minutes, seconds into decimal form. And that's all checkpoint number 4 was about, finding the cosecant of 34 degrees, 30 minutes, and 36 seconds. And you could do that in your calculator. I think I showed how to do that in the video. You can use the graphing calculator to just type it in and get a decimal answer. And there's a little blurb in section 4.1 that talks about converting between minutes and seconds into the decimal form. And they even point that out in the example in the textbook. But this is what that cosecant ends up equaling in that problem. All right. One thing I noticed, guys, is that there are some videos that end up getting not very many views from you guys. Part 3 video, I saw only 2 of you watched it, and there was a whole do now on it. So I thought that was a little bit humorous when all 11 of you answered that do now question and only 2 of you watched the video. So I was getting a little picky about some of the answers I was accepting for that do now. So several of you probably saw that I left a comment under yours, because a lot of you just listed the second and third identities without talking about how you get from the first identity to the second and third. So I fished that out of some of you, I noticed. But that video, actually, I think, talking about how those identities are used is probably one of the reasons why a lot of you struggled on the checkpoint for example 7, and maybe even numbers 47 and 51 in the quiz review, because they rely heavily on substituting and using those particular identities. For number 5, the checkpoint asks, based on the fact that cosine of theta equals 0.96, what's the values of the sine of theta and tangent of theta? These are the values, but do you guys know how you go about finding those 2 values?
Yeah.
Yeah.
No.
Not exactly.
No,
So
exactly.
in the textbook, they discuss a couple of ways. So if they're giving you the cosine of theta equals 0.96, I'm actually going to write this out in the problem here. The cosine of theta equals 0.96. What they want you to do is to use this information along with some of the identities, which I'm going to paste them into this particular set of slides, or all the different identities real quick, because we'll probably refer back to them a bit here. I think what I said in the in the video for this section from part 3 was that this particular set of identities, guys, this is one of those things I would tell you to put on a note card if we were in class and you were going to use something on the final or something in the future. This is something that I would say we're going to be digging this up quite a bit over the rest of this chapter and even the next chapter. So these reciprocal identities, the quotient identities, the Pythagorean identities, they're all going to be referred back to a lot. So with this particular problem, if they're telling you the cosine and they want you to find this one, which was the sine, I think, of theta, and this one, which was the tangent, you've got to, since you know what the cosine is and you're trying to find the sine, you got to look for a trig identity that involves exclusively just the sine and cosine. And the trig identity that involves exclusively just the sine and cosine is this Pythagorean identity, sine squared plus cosine squared equals 1. So we're basically going to use the identity as like a framework or a skeletal structure for how to find the sine. And we're going to write that in because we know this relationship is true. And I discussed how they got this identity in the first place in that part 3 video. It's all based on the Pythagorean theorem. But once you have this identity, since you know the cosine of theta equals 0.96, you can substitute that in right into this identity, which will leave you with oh, I don't want that to look like a theta. I'll just erase it. All right, so the idea is you plug in the 0.96, you're going to have to square it and then solve for the sine. So this becomes an algebra problem. You square the 0.96 and then you subtract it from both sides, and then you take the square root of both sides, and that's going to end up giving you the sine. So there's a whole bunch of steps that I just said out loud that you'd have to do on your calculator or on a piece of paper. This ends up equaling 0.9216. You subtract that from both sides, you're going to get 0.0784, and then you take the square root of both sides. Which leaves you with the 0.28. Okay, once you know the sine and the cosine, finding the tangent is going to be relatively easy because the tangent involves the sine and cosine right here. You just take whatever the sine is, divide it by whatever the cosine is, and that's going to give you the tangent. So to get this decimal, you just take 0.28 and divide it by 0.96, and that gets you the 0.2917. Does that make sense?
Yeah.
Okay.
I used to get it.
It's
No.
a lot of these identities are just being, all you got to do is find one that works, like use it as a framework and substitute stuff in to solve for what you're looking for. That's all example 5 was. I think example 6 was similar to that. For example 6, I think it's a same exact type of problem. They just tell you what the tangent equals. They said it was equal to 1/3 and asked you to find the cotangent, which was 1/2, and the secant, which was square root of 7. And for this one, if you know the tangent, and it's, they said, sorry, the tangent was 2. And they want you to find the cotangent. going from tangent to cotangent, since the tangent equals sine over the cosine, and cotangent equals cosine over the sine, whatever the tangent equals, you can just take the reciprocal of it, and that'll give you the cotangent. And that's why when you take the reciprocal of 2 over 1, it's going to end up equaling 1/2 for A. For B, to find they want you to find the secant. Tangent and secant are both used in the same trig identity exclusively right here. 1 plus tangent squared equals secant squared. So you plug in what you know for tangent, square it, and then add it to 1, and then take the square root of both sides to get the secant all by itself, and that's how you
I
get
dropped my
square root of
AirPod.
7. Well, I'm recording it, so if you missed something, you can always go back and watch it.
I thought B would be the square root of 5.
Did I write the wrong answer? Actually, I did write the wrong answer. You are correct, Amanda.
Hello?
Thank you.
Okay.
That is the square root of 5. I don't know where I got 7. Must have looked in the wrong spot. But yeah, it is the square root of 5. For that one. All right. Now on to example 7, this one, which I'm sure a lot of you were probably a little bit confused about. So these problems are just asking you to take one side of the equation and use identities like these to get it to look like the other side of the equation. So a lot of this kind of stuff is going to require you to substitute stuff that you know is equal to these and then simplify it to see how we can get it to secant. I actually dug up a what I consider sort of like a helpful guidelines cheat sheet, something or other, for these kinds of problems, which I'm putting up on the screen right now. This is not in your textbook, at least not in the textbook we're using. I got this from a different textbook that I've used in the past. And I find that these 5 suggestions really help with these types of problems. So if you're trying to get one side of the equation to equal the other side, first things first is it's easier if you go from more complicated to simpler. So when you're looking at a problem like this one, the more complicated side is the tangent cosecant, because secant's just itself. It's the most simple thing you're going to do. So changing from simple to complex is a little more difficult than from complex to simple. The second thing is, if you can, substitute one or more basic trig identities to simplify the expressions. So in our case here, we can take tangent and cosecant and replace them with a couple of different identities that are over here. We know that tangent is either equal to 1 over cotangent, or you can say tangent is equal to sine over cosine. So you can substitute tangent. You can plug this fraction in for this, or this fraction in for tangent. And for cosecant, there's really only one option up here that's simply cosecant. That's cosecant equals 1 over sine. I know cosecant squared equals cotangent squared.
Wait, are you moving? Like on the whiteboard?
I am moving on the smartboard, yeah.
It's frozen for me.
Anybody else got a frozen smartboard? I'll switch between some so that you can see. I'm jumping between some pages here.
See it, Alex?
What? Okay, wait. Okay, yeah, I see it now. I had to switch off.
Okay.
See,
So
I'm paying attention. Okay.
That's fine.
Sorry.
For cosecant, the only one that's plain cosecant is just 1 over sine. Cosecant squared, if you were doing an identity like this, you would need this to be squared to replace cosecant squared with this whole thing, 1 plus cotangent squared. So because it isn't squared in the first place, we're not going to replace it with this. We're just going to replace it with 1 over sine. So that's going to end up looking like this. The sine over cosine times 1 over sine equals this. And by doing that substitution, now you might see something here that can be simplified. Does anybody see anything here that can be simplified?
You could the
You can
sign
cross out
and
the
the sign.
signs.
Yeah.
Maybe put out.
Right.
Cross multiplied.
You can do some cross canceling. The signs are going to divide
Yeah.
out,
Second grade.
which all of a sudden it's going to look like this: 1 over cosine, and 1 over cosine. That's equal to secant. So I
we're
can
right.
just replace 1 over cosine with secant, and all of a sudden now the left side looks identical to the right side. So that's what these problems are trying to get you to do, is to take something on a complicated looking side on the left, do some substitution, and simplify from there to get it so that it looks identical. So this is the answer, or one of the possible solutions to part A. In the textbook, whenever you see these kinds of problems, like if you were trying to look up the answer in the back of the book for 47 and 51, the back of the book probably just said answers may vary, right? And the reason that answers may vary is because you could also tackle the right side if you wanted to. You could have made the secant equal to 1 over cosine and then changed it into this, which is a little bit harder to just organically create, and then go back to this. So there's more than one way to get there, is essentially one of the reasons why they label it like that. For part B of that checkpoint, you're starting off with this. Cosecant of theta plus 1 times cosecant of theta minus 1 equals cotangent squared. And once again, with this kind of problem, you're going to want to transform the more complicated side into the simpler side. So the more complicated side looks like the left side of the equation to me, because cotangent squared is all just one expression or one term. So what do you think we can do with this left side first that might help us with this?
Foil it.
Okay. Yeah. We're going to be foiling it this time. Now, in the last problem, we substituted first, right? So sometimes it's helpful to do some factoring or multiplying, this third suggestion here, in order to get the expression to look a little bit simpler. So sometimes it's useful to substitute. Sometimes it's useful to just multiply and get it a little bit more simple. So with no parentheses, if we do the foiling, you're going to end up with this: cosecant squared minus cosecant plus cosecant minus 1. And some of you at this point probably noticed that this is going to simplify to something. What can we get rid of from
The
this stuff?
cosecants, because one's a negative and one's a positive, right?
Exactly.
Yeah.
Those two go away. So it's going to end up being this.
That looks familiar, I think.
Yeah, now you've got cosecant squared minus 1 equals cotangent squared. That's much more simple than this. Now we can see maybe there's something we can do with this cosecant squared minus 1. So looking back here, cosecant squared, actually, we are dealing with cosecant squared and cotangent squared, and there's an identity that involves both of them. This one right here.
I think it's the same one, just like inverted.
Yeah. Now, that's the thing. This one doesn't look identical to this one, right? At this moment. But because this is an identity, everybody, you can actually subtract things from both sides and rewrite it, and it's going to be just as true of an identity. You can subtract 1 from both sides and have cotangent squared equals cosecant squared minus 1. So this is just as true of an identity as this. It just required you to subtract 1 from both sides. It's still equal. It's still right. But now you've got cosecant squared minus 1 equals this, which is identical to what our situation is right here. So since cotangent squared theta equals this, we can replace this with cotangent squared right here, and you're done.
Nice.
This is confirmed.
Nice indeed.
Okay, so these are some examples of those. Let me go back to the suggestions, because there's a couple more that weren't expressed in the checkpoints. One of them is to multiply expressions by an expression equal to 1. There's actually one of the quiz review problems involves this type of suggestion. So I'll revisit this in a bit. And then the last one is, I like to call this fifth suggestion, the break glass if necessary. It's kind of like the quadratic formula of verifying trig identities, where if you are stumped and you have no idea what else to do with the trigonometric identities, try to express all the trigonometric functions in terms of sine and cosine. If you are able to change everything into terms of sine and cosine, usually it's easy to see what to do next. It kind of actually happened right here in 7a when we changed tangent into terms of sine and cosine and cosecant into terms of sine. We saw that we could cancel the sines out, and all of a sudden it made it so easy to finish off the problem. So, all right, that's 7. We'll go over some more of those. I just want to give you guys the solutions to the checkpoints for 8, 9, and 10. So example 8's checkpoint was about 40 feet. This was 8, 9, and 10 were probably easy for you guys. At least I think they were, because they're all just SOHCAHTOA problems again. Problems you did in geometry. So 8 was 40 feet. 9 was 60 degrees. And 10, C was about 17.6, and A was about 17.2 feet. Did any of you have any questions about those 3 checkpoints?
I don't know yet.
Okay. All 3 of them were more or less just basic. You set them up like a sine of, let's see, the checkpoint for number 8, the angle of elevation of to the top of the flagpole at a distance of 19 feet from its base is 64.6. How tall is the flagpole? So you're going to be taking, let's see, the angle of elevation to the top at a distance of 14 feet. All right, 19 feet from the base. How tall is the flagpole? That's a tangent problem. You're going to be doing tangent of 64.6 equals the side you don't know. The side you don't know, which ends up being 40 feet over 19. And you, so let me just write that out here. The side you don't know over 19 feet. So this is a problem you did in geometry. Straight up, like this is all you did with trig and geometry, the SOHCAHTOA stuff. So you multiply both sides by 19, and then you plug the left side into the calculator, and that gives you this answer. All 3 of these problems were more or less just like that. Number 9 was find the acute angle theta between the 2 paths as shown. They give you a picture. This is one where you needed to use the inverse cosine, because you're dealing with adjacent over hypotenuse. And that's going to give you your angle. And when you plug this in the calculator, it ends up giving you 60 degrees. And for 10, they give you a diagram there. To get C, it's sine of your angle, 11.5. And that's going to be equal to 3.5 over C. And to get C by itself, you're going to multiply both sides by C and then divide both sides by sine, and that'll get you the C. You plug 3.5 divided by sine of 11.5 into your calculator, and that gives you that answer. To get A, you can use tangent, because you have the opposite side, which is 3.5. And you're trying to find the adjacent side, A. And so it's the same kind of problem as this one. Multiply both sides by A, divide both sides by 11.5, and then plug 3.5 over this into your calculator to get that.
All right, gotcha.
All right?
Use
So that's
my
the
cat.
checkpoint problems. Do I have any questions about those before I move on to the quiz review?
I'm good.
No, I don't think so. I'm good.
Awesome. If you do have a question, you can type in into the chat window, or you can just interrupt me. Just let me know. So the first quiz review question was number 11. These solutions, a lot of the solutions for the odd problems, I tried to assign a lot of odd problems so you could just look up your final solutions in the back of the book to check your answers. So these 6 were in the back of the book. Did I have any questions about 11?
Oh, shit. Mr. Walter,
Yeah.
I have another class to go to in like 10 minutes.
Uh-huh.
Just letting you know.
Okay. Well, I'm still recording this, so if you missed the
Okay.
last part of it, you can always I'll put it up on YouTube so you can watch it later.
Okay.
If there's a question you'd like me to prioritize, I can talk about that.
No, it's okay. Just keep going how you were going.
Okay. So
Sorry for
the
interrupting.
other thing about number 11 is they say the triangles are similar and corresponding sides are proportional. So you guys might remember from geometry, one of the questions in this for number 11 is explain why the function values are the same. When you have similar triangles, the ratios of the sides are all going to end up reducing to the same thing. That's more or less the answer to that question. So that's it for 11. The next one was 19. 19, they gave you the sine of theta equals 1/5 and wanted you to find the other 6. This problem, they recommend sketching a right triangle corresponding to the trig function and then labeling things. The idea here is if you, let's just create a general right triangle here. All right. For the sine of theta, if you said this was theta, the sine of theta was 1/5. So the 1 has to be the opposite side, the 5 has to be the hypotenuse. Based on this information, you can figure out what this side is. There's a couple ways to do that, but the main way you could possibly use is Pythagorean theorem. And then simplify this. Subtract the 1. Take the square root of both sides. Simplify this. Which gives you 2 squared is 6. If you want to know how that happened, I'll refer you back to what we learned in the radical simplifying square roots chapter, where you just take this and find a factor that's a perfect square. In this case, I found this to be the square root of 4 times the square root of 6. And since the square root of 6 only has factors of 2 and 3, none of those are perfect squares. You can't simplify that, but you can simplify the square root of 4. So you get that. And then, since this is opposite, this is hypotenuse, and this is adjacent, you can figure out all 6 of these. Like cosine is just adjacent over hypotenuse, square root of 2, or 2 square root of 6 over 5. That's how we get that. Tangent is opposite over adjacent, 1 over this. So you'd have to rationalize the denominator here. To get that solution. The square roots of 6 become square root of 36, which is just 6. 6 times 2 is 12. That's how they get that. Cosecant is hypotenuse over opposite. That's how it gets the 5. This is just the reciprocal of this, and then you rationalize it. This is the reciprocal of this. That's how you get that. All right. Number 33. 33, you can do those two in the calculator. You just plug in the cosine of 4 degrees. If you go, let me pull up the calculator. I've got the emulator on my computer right now. I think I did this in part 2 video. So if you need to kind of see another example of this, it's in the part 2 video from this past week. 2 weeks, technically.
It's been a while.
It's up there on YouTube. It's also on the Google Classroom if you need to refer to it.
Are all your videos unlisted? Because
They are, but you can find them all in the
Okay.
Google Classroom under the online notes and yeah, let me see. They should all be, when you go on Google Classroom, you can go under classwork, and I have a section called online notes and videos. I don't know if you guys have access to that on the app, but I'm pretty sure you do.
yeah, I think so.
Google Classroom. Yeah, all the videos, like I have section 4.3, part 1, part 2, part 3, part 4, and part 5 all up there.
Okay.
So you can go back and look on those on your phone even and pull up the YouTube videos from there. So anyway, let's slap this up on the screen. So the question for this, for 33, is to find the cosine of 4 degrees, 50 minutes, and 15 seconds. So in the video, I demonstrated you could do this by, where's it? Yeah. You hit the cosine button. You can do 4 degrees by hitting 4 and then hitting the second and the apps button. And that brings up the angle window, which shows degree and minutes here. So you can type 4 degrees, then do 50 minutes by going back here and doing this spot. And then 15 seconds. The second button is actually, if you hit alpha and then the plus sign, that gets you that. And then you can just hit enter and it'll give you the decimal version. So that's all you had to do for 33. Just type something like this. Part B says find the secant of this angle. To find the secant of this angle, the same exact angle, you do 1 divided by this answer.
Your screen is now black for me. Is it like that?
Is it?
Yeah. I thought you were like doing that.
Ah,
Okay.
Let me
You came back
stop
for like a
presenting.
second.
Let me stop presenting, and then I will represent.
Okay. See the calculator.
So there you go. So
Okay.
let me demonstrate this once again. Does this? I'll do it one more time. You do cosine. This one is 4 degrees, so you hit 4, and then you can hit the second and the apps button, and that gets you this. And there's the degree marker. So you can get 4 degrees, 50, and then you need the minutes, which is the second option on angles. And then to get the seconds for 15, you hit alpha and then the plus sign, and that'll give you there, because there's the minute sign. And then enter, and that gets you that. And then to get part B, you just do 1 divided by that answer. And that's how we get those. Now, if I pull up the smart board, can you see the smart board again?
Not yet.
No, I'm
Mr.
on the
Walter.
calculator right now.
It's still in the calculator.
Okay. I'll stop presenting and represent to get back to this smart board. I had that same, I found out that I had a similar issue when I was making YouTube videos. I was pulling up the calculator and I was talking through how to do a problem on the calculator, and then I went to edit the video and found out that I was just talking about it, and it just left up my my notes. It wasn't doing anything else.
What do you use to record?
I use the there's a overlay option with Microsoft where you can hit the Windows button and G at the same time, and it lets you record your screen.
Mm-hmm.
My computer's having some issues right now. I'm waiting on it.
Mr. Walter, I have to go to Miss Patrick's class.
Yeah, me as well.
which is
And Marv does too, but
Yeah,
One
I
minute.
might, but
Well,
I want to see if I could do 2 at a time. I'm gonna try it.
YOLO.
Oh yeah, I can. I'm in 2.
Okay.
No one's there, so I'm just chilling.
well, I can't do 2 at a time, so I will
She called me. Wait,
watch
Alright.
this later as I go to Miss Patches.
Yeah, I will also watch this later. Okay. Goodbye. He's black screen.
Marv said, "Uh-oh, she called me."
Oh, I can do both at the same time? That's cool.
What happened?
Mr. Walter.
He did say his computer was having trouble.
hey everybody. Sorry about
He's
that.
back.
I don't know why, but
Welcome
my
back.
computer was freaking out there for a second.
Mr. Walter, I'll see you another time. I gotta go.
That's fine. I'm gonna keep going with the rest of these examples. You guys can, if you missed it, you can watch the rest on YouTube. All right.
Okay, sounds good. I'll see you.
All right. Let me get back to the Smart Notebook. All right. So that's 33. There's your answers. 39. Did anybody have any issues with 39 or 41?
Yes.
Okay. These problems were very similar to the problems number 5 and 6 as the checkpoint problems. The whole idea with these for 39 and 41 was if they give you the cosine of theta, which equals 1/3. Each of them are asking you to find a whole bunch of different options. So for part A, it's asking for the sine of theta. So to find the sine of theta, you're going to need to use the trig identity that uses sine and cosine, which is, let me erase this. This one. It's the only one that involves just sine and cosine. So for this, you'd have to do the sine squared of theta plus the cosine squared of theta equals 1. And then since cosine of theta equals 1/3, you can plug that in for cosine here. 1/3 squared is going to be 1/3 squared, which is 9, 1/9. Subtract the 1/9 from both sides. To get 8/9, and then take the square root of both sides. And that's how they get the square root of 8 over the square root of 9. The square root of 9 is 3. The square root of 8 is the same thing as the square root of 4 times the square root of 2. And the square root of 4 is 2. And that's how they get 2 square root of 2 over 3 for A. And a lot of these kind of follow suit in a similar format. B is the tangent. So to get the tangent, you just got to take the sine, this fraction, divided by the cosine, this fraction. And that's going to be a keep, change, flip scenario. Keep the first fraction, change this to multiplication, flip this one. And that's going to look like this. And you'll probably notice the 3's go away. And that's how you get 2 square root of 2 for B. For C, it says the secant of theta. The secant of theta is the reciprocal of this one, because cosine is the reciprocal of secant. Just flip this fraction, you get 3. And then D, this one is one that I didn't really do an example of before. The cosecant of 90 degrees minus theta. which is a cofunction. So if you go back in your textbook, let me see if I can pluck that particular set of stuff from the textbook real quick here. The cofunctions were listed in your textbook.
I have a
And they
question,
look-
Mr. Walter.
Yes, Mikey.
So when me and Marv were doing the quiz review yesterday, we were doing 33 and, 39 and 41. Does it have to be in the radical form, or can we do decimals? For like sine, we got 0.9428, and it equals the same thing.
No, you can write it in decimal form.
All right.
I left it. Well, actually, you know what? I'm sorry. Technically, it has to be in fraction form because in the instructions they use the word exact value.
Okay.
The exact value requires you to not be rounding a decimal. And since the decimal version that you presented, although it is the beginning of the representation of this fraction in decimal form, you need to have the actual fraction for it to be the exact value, because it's the decimal's just going to keep going on and on and on and on and on and not repeat and be a irrational number. And if you round it and just give me the first few digits of the decimal, it's not exactly this.
Okay.
So because they use that phrase, the exact value in the instructions, you would have to find this. But you can use the decimal that you got, Mikey, to check your answer for certain.
Okay.
For certain. And if you, I think I mentioned in one of these videos, it might have been from the last section, that oftentimes you can use the decimals. If you see a lot of these decimals often enough, you might recognize what their fraction value is supposed to be.
Yeah.
Like
I remember.
if you looked at that decimal and you figured out, okay, that might be a multiple of the square root of 2 or the square root of 3, you might be able to just guess and check on a calculator and figure out what the fraction form is. I don't know if these calculators could make 2 square root of 2 over 3 into a. Let me see here. I'm doing this on my calculator that I have in hand. So if I got the decimal form of that, you know how the calculator has the ability to change something back into a fraction sometimes?
Yeah.
Yeah, this one doesn't have that ability. It doesn't. The calculator probably just doesn't like irrational numbers very much.
Alright.
So,
Well, I can do that. I'll keep a fraction then.
okay, let me talk about D real quick, because D involves these cofunctions. So in part D of 39, they ask you for the cosecant of 90 minus theta. Well, on what page is it in the textbook? Page 279 in your textbook, this diagram is put up. This is another one of those. I would tell you to put this on a note card for future reference kind of situation. And it turns out that they're asking you for this in part D, the cosecant of 90 minus theta, which is equal to the secant of theta. So if they're asking you for this, they're also technically asking you at the same time for this. So this might be more confusing, but you can substitute it for this. Cosecant of 90 minus theta is equal to the secant of theta. And in this case, the secant of theta was actually asked for in part C. Part C was the secant of theta. And if part D is equivalent to the secant of theta, it's going to have the identical answer, which is why 3 is the answer for D. If you want to know more about how these cofunctions were created, I go into explanation about it in the part 2 video from the notes of this week. I did a brief discussion of how they arrived at these particular expressions, but they are very useful. In fact, for part C of number 41, part C is another one of those where it's cotangent of 90 minus, they say alpha, but it's really an interchangeable variable in this case. The cotangent of 90 minus your angle is equal to the tangent. And the tangent of your angle for number 41 was actually asked for in part A. That's why part A and C have identical answers for number 41. And part A you find from this one because they tell you the cotangent of alpha is equal to 3. And tangent's just the reciprocal of this. Reciprocal of 3 over 1, which is 1 over 3. B and D are related to one another since B is cosecant and D is sine. Cosecant and sine are reciprocals of one another. So once you find one, just take the reciprocal of it to find the other. So for I'll just do part B real quick because cosecant, which is what they're asking for in B, and cotangent, cosecant and cotangent are related in this trig identity. 1 plus cotangent squared equals cosecant squared. 1 plus cotangent squared equals cosecant squared. And so you can just plug in 3 here. 3 squared is 9. These two add to make 10. Take the square root of both sides. That's how you get square root of 10 for part B. And then for part D, this is just square root of 10 over 1. You flip that for part D, and then you rationalize it. Square root of 10 times the square root of 10 is the square root of 100, which is 10. That's how they get D. All right. Any questions on those? Does that make more sense for you guys? I know you said some of you were tripped up with a few of those.
Yeah, this clears it up a lot.
Okay. So let me get to 47 and 51. Because 47 and 51 do more of this. 47, they give you this. This one actually looks very similar to the one we did in the checkpoint. And it's going to have a similar first step. You've got like a binomial times a binomial. You can FOIL it to get this. These signs are going to subtract or add out if you want. And then this particular side of the equation is another one of those just... where did I put it? There it is. It's just another one of those manipulations of one of the identities. You can take this identity and let me bring this down here for a second so I can refer back to it a little bit easier. Since we're dealing with 1 minus sine squared, if you subtract sine squared from both sides here, that'll go away. Cosine squared is equal to 1 minus sine squared. So you can just substitute for 1 minus sine squared. In this case, 1 minus sine squared is just going to equal cosine squared. And that's going to be done for 47. And then 51. This is one that I was saying earlier, you're going to have to use the fourth suggestion right here. Multiply expressions by an expression equal to 1. And the reason for that is you're adding 2 fractions here on the left side with unlike denominators. And if you were adding something like 1/2 plus 1/5, you would have to come up with a common denominator. In this case, if it was 1/2 plus 1/5, the common denominator would be what? Do you guys know? 10, yeah. It's just you take the 2 numbers and multiply them together, right? So you get 2 times 5 in the bottom and 2 times 5 at the bottom. But you can't just change them both to 10. You got to manipulate the numerators too. If you multiply this by 5, you got to multiply this by 5. If you multiply this by 2, you got to multiply this by 2. And all of a sudden now you've got like denominators, you can add the numerators. It's a similar situation here. the like denominator for cosine sine is just the two of them multiplied together. So what you're technically doing here is multiplying the, like in this scenario, you would multiply the top and bottom by the 5, which 5 over 5 is equal to 1. And that's what it's referring to here, multiplying expressions by an expression equal to 1. If it's equal to 1, that means, wrong slide, something like this, 5 over 5. And in this case, it would be 2 over 2. Those two are both equal to 1. This right here, the sine over sine is equal to 1. And this right here, the cosine over cosine is equal to 1. So you're technically not changing the value of either of these fractions if you're multiplying it by this over this, the sine over sine and the cosine over cosine. But what it allows you to do is it allows you to have this like denominator. These both are sine cosine now. So once you have those like denominators, you'll be able to add the numerators together. So once you multiply both sides, or not both sides, both fractions by something equal to 1, you might notice sine times sine. What's that equal? Anything times itself. What's sine squared? And cosine times cosine is going to give you cosine squared. So we can simplify those numerators into that. And now, since you have like denominators, you can add the numerators together to get this. Sine squared plus cosine squared in the numerator over your like denominator. All right. We've technically simplified this a little bit, but does anybody recognize something about this numerator? What can we replace this numerator with?
Technically,
Yeah.
1.
The sine squared plus cosine squared, this part right here equals 1. So you can go ahead in this step and just replace that with 1. And now you've got 1 over sine times cosine. And this, you can actually separate into two fractions. 1 over sine times cosine, when you've just got 1 in the numerator, this is the same thing as 1 over sine times 1 over cosine. These are equivalent. And you might recognize now you've got 1 over sine and 1 over cosine. Those are both equal to cosecant and secant, which are exactly what you want right here. 1 over sine is equal to cosecant. 1 over cosine is equal to secant. And there you go. You get identical sides to those equations. All right. So let me, I'm just going to put this back right here. These are the 5 I would suggest you write down or put down in your notes or something, because it'll be very useful for you on the quiz. It'll be useful for you in the upcoming sections in the future. I might even refer back to it in the future a little bit myself. But that is the case for those two problems. So now I think I've only got 3 examples left, or 3 problems from the quiz review. Number 57, which is not too difficult. It says to find each value of theta in degrees and radians without using a calculator. So this one, for number 57, they just want you to be able to use the unit circle from like the last chapter to figure out what the cosecant of theta, equals 2 square root of 3 over 3. They want you to figure out what angle will make this happen. And in this case, if you look on the unit circle that we did in the last section, this is a terrible unit circle. Let me redo this. Okay. Then we'll make a nice looking circle. That's a little better. You'll find out that up here, this 60-degree angle has the coordinate points that you're looking for. One 1/2 for your x, and square root of 3 over 2 for your y. And cosecant is just 1 over your y value. And since this involves the square root of 3, it's probably involving a square root of 3 over 2 coordinate. When you do the keep change flip, this is going to end up equaling 2 over the square root of 3, which you can then rationalize. And it's going to end up equaling that. And part B is very similar. Part B is asking for the sine of theta equals square root of 2 over 2. That one's pretty obvious. You're looking for an angle that is acute based on the instructions that provides a y value of square root of 2 over 2, and that's just the angle 45 degrees, which has square root of 2 over 2, comma, square root of 2 over 2 as your values for y and x. All right, 65 and 68. Did anybody have any problems with 65?
No.
Yes.
I hear a yes.
That John was confusing.
All right. So 65, you were skiing down a mountain with a vertical height of 1,500 feet. And the distance from the top of the mountain to the base of it is 3,000. Oh, wait. No, this isn't the right problem. In the textbook, this isn't 1,500. This was 1,250. And this wasn't 3,000. This is 2,500. How odd. All right. Well, vertical height is 1,250. The distance from the top of the mountain, let's say this is the top of your mountain, to the base is 2,500 feet. So 2,500. That's the straight up distance to the bottom of the mountain. And then they say, what's the angle of elevation from the base to the top of the mountain? That's this angle right here. All right. So if this is our scenario, based on our angle, this side right here is your opposite side. This right here is your longest side, your hypotenuse. So which trig ratio, if you're using SOHCAHTOA, which trig ratio goes with opposite and hypotenuse?
Sine.
Yeah. So you're just taking the sine of your angle, which is equal to 1,250 over 2,500.
That equals 1/2.
Right. So you're just looking for what angle when you take the sine of it gives you 1/2. You can use your unit circle to figure this out, or you can even do inverse sine of the 1/2 to find the angle.
It's 30 degrees.
Right. And that's going to end up equaling this 30 degrees, or pi over 6. Okay? That one wasn't too bad. 68 might be a little bit tougher. Some of you might have had some trouble with 68. All right, 68. Let's make sure that this one has the same stuff, because the last one, they changed something slightly. I think this is right. So they give you this diagram. They ask you, or they tell you you're traveling across a flat land. You notice a mountain directly in front of you. Its angle of elevation to the peak is 3.5 degrees. That's this one. After you drive 13 miles closer, so you get to here, the angle of elevation is now 9 degrees. Approximate the height of the mountain. All right. So one thing that you got to keep in mind is they're talking about this vertical height, which is going to have a 90-degree angle here. So we've technically created two triangles, two right triangles. But this height is not changing for either of those triangles. There's an unknown distance from this point to this point here, from here over to here. That's x. But we do know this distance right here is 13. So our goal is to find the height of the mountain. We want to find out what h is. So in this case, the easiest way to do this is to kind of set up a couple of trig ratios based on the information we have. If we look at it strictly from the sense of the 9-degree angle, the height right here is your opposite side. And the x value right here is your adjacent side. Which trig ratio uses opposite and adjacent from SOHCAHTOA? Do you know?
I think it's cotangent.
Cotangent uses opposite and adjacent, and so does tangent. It just depends on which one you want in the numerator and which one in the denominator. I'm going to stick with tangent because we have calculator buttons for tangent. Tangent of your 9 degrees is going to equal h over x. All right. Not much we can do with this because we got two variables. We can't solve for one variable if we don't know the other one. So let's see if we can make another or different trig ratio. But this time, let's talk about it in terms of the... I didn't want to do that. I want a small eraser. Let's talk about it in terms of this bigger triangle that has 3.5 degrees. If we're going from the 3.5 degrees, this h is still the opposite side. I'm talking about this triangle right here, by the way. All right. From the 3.5 degrees, h is your opposite side, but your adjacent side is this whole thing, which is the sum of 13 and x. So we can actually create another equation.
Mr. Walter,
Yes.
I have to go to Miss Chapel's meeting now.
All right. You can check back in for the recorded answer, and then hopefully that'll help you out here.
Was it 1.3?
Yes.
Okay.
Okay.
I missed
So the for everybody else here, we've got to solve for h, but this is one of those situations where we have two equations and we've got to get rid of one of these variables so we can get h. Fortunately for us, we can rewrite each of these in terms of h by multiplying both sides of this equation by x. And same thing with this one. And since these both equal h, you can set these equal to each other. That's where we're going here. This is a longer problem. All right, now that you've got them both like this, you can actually do some simplifying. You can distribute this to both terms. Plus 13 tangent, running out of space. All right, I need some more space here. All right, let's see. Let me rewrite this. X times the tangent of 9. No, 3.5. Nope, 9. I was right the first time. Equals these two. 13 times it. Yeah. All right. There's a lot going on here, but it might not be obvious how you can get x by itself at this point once you've distributed the 3.5. So let me just point out to you that both this term right here and this term right here have an x, and this one doesn't. So if you get the terms with the x's on both on the same side, you can factor the x out of both of those terms. So I'm going to subtract x tangent of 3.5 from both sides. It's going to look like this. X times the tangent of 9 minus x times the tangent of 3.5 equals 13 times the tangent of 3.5. And once you're here, both of these have an x term that you can factor out. So you're going to get x times the tangent of 9 minus the tangent of 3.5 equals 13 times the tangent of 3.5. And then you can actually get x by itself by dividing both sides by this, the tangent of 9 minus tangent of 3.5. Those cancel out. You're going to be left with x equals this big giant fraction. And this is actually something you can plug in the calculator and get a decimal answer for. So that's going to tell you what x equals. And back in the original problem, we can figure out what h equals if we just take what x equals and multiply it by the tangent of 9. So down here, h is going to equal this 13 times the tangent of 3.5 over this multiplied by the tangent of 9. Because tangent of 9 is equal to, well, tangent of 9 is right here in this part of the problem. X is what we just solved for, so h is going to be the result. And when you take 13 times tangent of 3.5 and divide it by tangent of 9 minus tangent of 3.5, and then take the result of all that and multiply it by the tangent of 9, it's going to end up equaling about 1.3 miles. I know, it's a big, long problem. You're not likely to see something maybe that complex on the quiz, but I'm not going to say you may never see that kind of problem again. So I just wanted to make sure you guys saw that problem and got a chance to do that. All right, for the three of you left here, do you guys have any other questions about the quiz review or the checkpoint answers that I haven't talked about already?
I
No.
think that just about clears it up.
All right. The quiz is going to be posted in a little bit. And like I said earlier, I'm going to be making that quiz due later in the evening on Monday. So, and I'll set up a Google Meet. So if you start doing it, if you start doing the quiz and you look at some problems and, you know, you try some, but you don't finish because you're confused on one or two of them, you can pop on Monday and just ask me in a setting like this one, and I can maybe give you some hints to help you out with that. All right?
Sure thing.
Okay.
All right, everybody.
All
So
right.
I'm going to stop the recording now, just so you know. Just gonna stop that.